are presenting our research on energy and Laplacian energy of the relative Coprime graph of symmetric groups for degree 3 and 4. Hi, my name is Nurzurin Iwani binti Hashim.
Hi, my name is Muhammad Alif Haikal bin Mohtar.
And together with my team members, Dr. Noarida Abdurrani, Dr. Fadila Nur Mahia Abdul Manaf, and Madam Masnira Ramli, now let's move on to the details of our research. Research on Coprime graph has been more extensive compared to relative Coprime graph. Most prior studies have focused on specific groups, such as dihedral and quaternion groups, but there has been little attention given to symmetric groups in this context. This creates a gap in research as there is limited study on relative Coprime graph of symmetric groups, particularly for degrees 3 and 4. To address this gap, our study aims to construct the relative Coprime graph for symmetric groups of degree 3 and 4, compute the energy and Laplacian energy, and analyze the relationship between these energies. Our study is guided by the following objective. First, to construct the relative Coprime graph for symmetric groups as n where n equal to 3 and 4. Second, to compute the energy and Laplacian energy of the relative Coprime graph of symmetric groups as n where n equal to 3 and 4. Third, to compare the results of both energy and Laplacian energy. Scope of project. The study focuses on constructing and analyzing relative Coprime graph of symmetric groups S3 and S4 using subgroups properties. The project aims to compare the structural differences of this graph by computing and evaluating the energy and Laplacian energy. The study is limited to S3 and S4 and does not extend to higher degree symmetric groups or real-world application. This is our project flowchart. It consists of 3 phases. In phase 2, there are 2 steps. First, finding the energy, and second, finding the Laplacian energy.
This table shows 6 elements in S3 can be proved by 3 factorial equal to 6. And this table is shown 24 elements in S4 can be proved by 4 factorial equal to 24. And we can identify both subgroups by determining a subset that includes the identity and is closed under the group operation. And for the phase 1 is we construct the relative Coprime graph for symmetric group S3 and S4, which is vertices is elements of S3 and S4, and for the edges is connect vertices if their element orders are relatively prime. So this is our relative Coprime graph for S3. This is our relative Coprime graph for S4. In phase 2 step 1, we calculate the energy of the graph. We take the graph K1S3 as our example. First, we compute the adjacency metric, which is n times n metric, where n represents the number of vertices in the graph. Since S3 has 6 elements, the adjacency matrix will have dimensions 6 times 6, where each entry indicates a connection between elements based on the relative Coprime graph. The resulting adjacency matrix show the element 1 connected to all other elements and no other direct connection among 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Once the adjacency matrix is determined, we compute its eigenvalue by using block diagonalization. The eigenvalues for energy denote as lambda. The energy of the graph is then calculated using the formula energy equal to summation lambda I. Based on our calculation, here is the final energy value for K1. Next, in step 2, we calculate the Laplacian energy of the relative Coprime graph. To do this, we first determine the Laplacian matrix where the diagonal entries represent the degree of each vertex and the non-diagonal entries show the connections between elements. Once we compute the Laplacian matrix, we find its eigenvalue denoted as mu, which are shown here. To calculate the Laplacian energy, we use the formula sum mu minus 2m over n, where m is the number of edges and n is the number of vertices. Now we apply this formula to our compute eigenvalues, and here is the final result for the Laplacian energy. Now, let's go through the results of our study. For S3, subgroup with more elements and complex permutations have higher energy values. This means that as a subgroup grows in complexity increases leading to higher energy. However, Laplacian energy in S3 remains fairly stable, with only a slight increase as more elements are added. Subgroup like K1 have lower values, while larger subgroup like K2, K3, and K4 show slightly higher values. For S4, the energy values are much higher due to its large size and complexity. Subgroup like H29, which contain multiple permutations, have the highest energy. The Laplacian energy in S4 also varies widely. Simpler subgroup like H1 have some lower values, while complex subgroups such as H22 to H29 have significantly higher values. This shows that Laplacian energy in S4 is more sensitive to subgroup complexity, leading to greater variations compared to S3. And here is our conclusion. This study successfully achieved all three research objectives. The results indicate that S4 exhibits higher energy values due to its larger structure and increased complexity compared to S3.
Commercialization potentials. When it comes to cryptography, symmetric groups strengthen encryption, securing communication and blockchain. As for network science, Laplacian energy enhance cybersecurity and IoT security. Moving to quantum computing, this group refine quantum circuits, enabling quantum-resistant cryptography. In the field of molecular chemistry, spectral graph theory support AI-driven drug discovery. Meanwhile, artificial intelligence benefits from symmetric groups, improving big data analytics. Novelty of research. This study provides new mathematical insight for S3 and X4 in spectral graph theory, exploring an unexplored calligraph and linking this finding to cryptography, quantum computing, and network science. It generalized to higher order groups and introduced new computational algorithms, significantly advancing both theory and practice.
Thank you for watching and listening to our presentation. Bye!